This is applied physics course for undergraduate students, and we are going through the chapter 5. I am Dr. Nasir Mirza, and today we will be talking about the applications of the Newton's laws, and its part 2 lecture. The first lecture is already available. Let's move further to the Newton's laws applications, and we have already seen that the normal force, which is whenever there is a contact, when there is a reaction of the both bodies, and both of them have the reaction forces. And for example, a book, when is resting on a table, as shown in this figure, the gravity is exerting a force which is in the downward direction on the book, but the book has no vertical acceleration. There is a force, but there is no vertical acceleration. So this vertical force, the net vertical force, is zero. And how it is zero? Because there is an additional upward force which is acting on it, and this additional upward force is actually the normal reaction force exerted on the book by the table. So it is not the reaction of the earth, it is the reaction of the table. Table is not allowing this book to go down and get accelerated. So this normal means that it is always perpendicular to the place where the two bodies are in contact with each other. So whenever there is a object resting on the other object, it means that there is a normal reaction force. And in a free body diagram, this normal reaction force is shown as N against the weight. So even though the normal force shown in the free body diagram of the figure is equal and opposite to the weight, but it is not the reaction force due to the weight. The weight is basically the force which is exerted by the earth on the book. However, the reaction force is the force which is exerted by the book on earth. But the N is a normal force, which is a normal reaction that the table is showing to the book. So reaction to the normal is the downward force by the book on the table. So what I can say that if there is an applied force on the book in the downward direction, then the total downward force will be the weight of the book plus the force which is further exerting. And so normal force will become more. It will be more than the weight of the body. It will be weight plus the force which has been applied, because still the book is stable on the table. Therefore, the balance of these two forces is taking place. So we can safely say that the tension and the normal forces are the examples of the contact forces. Whenever two objects are in contact with each other, the tension can be there and the normal forces can be there. Let's do one example on this. And this is a sample problem in which a block of mass K, M, for example, has been omitted, is held in this place by a string on a frictionless plane, which is inclined at the angle of 27 degrees. Question is to find the tension in the string and the normal force exerted on the block. So what will be the normal force exerted on the block by the plane, and we have to analyze subsequent motion after the string is cut. So first we solve this using the free body diagram, and let us make a free. The best thing is that we must have the coordinate system also a little bit tilted. This tilted coordinate system is shown here as X and Y coordinate system. You can see X is now parallel to the inclined plane. So free body diagram shown here has the choice of the coordinate system with the x-axis along the plane, and the y-axis is a perpendicular to the plane, inclined plane. And the block is attached to a string, and block has a normal force acting on it, and then there is a weight which is perpendicularly downward, and there is a tension in the string which is away from the body as shown here. So we move further to decompose. Once we try to decompose the force F, which is the weight due to the gravity mg, also written here as W, then the angle theta is shown here. We can establish this, that this angle, the 27 degrees, is the same angle in between the perpendicular y direction and the weight of the body. If this angle is theta, then the component of the W, the mg, along this y direction will be mg cos theta. And the component along the x-axis will be mg sine theta. Then resolving these component into x and y components, we can see here that t is in the positive x direction and mg sine theta is in the negative direction. So t minus mg sine theta is the sum of the forces along the x direction. Sum of the forces along the y direction is there is a normal force n, and there is a mg cos theta in the downward direction. So n is with the positive sign, and the mg cos theta is downward, therefore it has a minus sign. Then we can apply the Newton's law, which says that the net forces must be equal to the mass time acceleration. So along x-axis, the sum of the fx is m into ax, and sum of the forces along the y direction is equal to mass times ay. However, the body is at rest. It is not moving. Therefore, the acceleration is zero. Therefore, the component of acceleration along x and y direction both are zero, and therefore we have the simplification. Now we substitute the value of theta as 27 degrees and reduce these equations to find out tension T and the normal force. It is 80 newtons and 157 newton respectively. The mass has been substituted as 18 kilogram, and G value is 9.8 meters per second square. Now the question comes, when the string is cut, the tension disappears. Then T becomes zero. Because you cut the string, then this tension is gone. T is gone. If T is zero, then mass accelerates downward. It starts moving downward. So T minus mg sine theta and minus mg cos theta plus n, these two equations become 0 minus mg sine theta equal to mass time acceleration, and minus mg cos theta plus n equal to m into ay. Now we know very well that there is no acceleration along the y direction, therefore ay will be 0. And simplifying this, we get the n equal to mg cos theta, and we substitute the value of theta and the value of m and value of g, we get 157 Newton. Ay is equal to minus g times sine theta, and we substitute and get the acceleration as minus 4.45 meters per second square, and this negative sign indicates that it is accelerating in the minus x direction, the downward direction. In the limit that this angle theta becomes 0, you can see here that the sine theta becomes 0, therefore ax becomes 0. So when the angle is 0, the acceleration will be 0. And if the angle is 90 degrees, then the sine of 90 degrees will be equal to 1, and the acceleration will become minus g. It will be a body which is free falling downward, and it will have only the gravitational acceleration. So it will become minus g. So the answers are consistent with the reality, and so it is a physically realizable answer. Therefore, we have proceeded nicely and the problem has been solved. This example is about the Atwood machine, and this machine is a very simple thing, and it has a unique application in well-known elevators, and in many cases where you want to pull water from a well, or you have uh, mm, uh, a system in which you are using pulleys and the carts to drag mass. Here we show a particular example in which the two blocks of unequal masses, M1 mass and M2 mass, are shown, and they are attached to a string, which is one string, and they are connected, they are passing through a pulley, ideal case pulley, and it is attached to the ceiling. The pulley mass is negligible and it rotates with a negligible friction, and M1 and M2 masses are different, and M1 is smaller and M2 is greater. So the arrangement is called Atwood machine, and its question is that we need to find out the tension in the string and the acceleration of the blocks, if any. So we choose our coordinate system such that the positive y direction is in upward direction and x-axis is along the horizontal direction as shown here. So we make the free body diagram for the mass M1 and for the mass M2. We can have many other diagrams, but these two will do a good job for us to solve the problem. Net force along the y direction is always there, but the x horizontal components are not here much visible. So we do not go further for the x part. Once we look into the mass M1, we can see that away from the mass is the tension T1 and downward force is M1 into G. Similarly, for the M2 mass, the away from the mass M is the tension T2 and the downward force is M2 into G. Therefore, if we choose coordinate systems and decompose and only focus our attention to the y component of the force, then we need to have this net force along the y direction for M1 and M2 as T1 minus M1 into G. The minus is due to the fact that it is in the downward direction. Similarly, sum of the y forces for the mass M2 is T2 minus M2 into G. Then further, the net force along the y direction for M1 and M2 are these. Then applying the Newton's laws, we see that M1 A1y, M2 A2y are the forces the equal to the net force. Now the tension has the same magnitude everywhere in the string. So it is not T1, it is not T2, it is simply T. Similarly, the acceleration along the y1 and y2, this is same for the mass M1 and mass M2, and it is equal to, say, minus A. Therefore, we write it down as A or minus A. Then we have A and minus A, the upward acceleration and the downward acceleration. The heavy mass will be coming down and the lighter mass will be going up. Therefore, we substitute these values, and adding and solving, we get the tension and the acceleration values. Since there were only two unknown involved, the tension and the acceleration, the two equations were just enough to solve the whole problem. Now let us add one more concept. In addition to the normal force concept, there is frictional force. whenever the surface of one body slides over that of another body, then each body is exerting a frictional force on the other. The frictional force on each body is in the direction opposite to its motion relative to the other body. Remember, frictional force is always in the direction opposite to the motion. The frictional force automatically opposes the relative motion. The frictional force acts between the surfaces that are at rest with respect to each other. Such forces are called static frictional forces. The force acting between the surfaces in the relative motion are termed as kinetic friction. So if there are two objects placed on each other and we intend to move one with respect to the other, then there is a static friction. Before the start of the object, the static friction is always there. And if the body starts moving, the moving body always keeps on feeling certain friction, and that is the kinetic friction. The ratio of the magnitude of the maximum force of the static friction to the magnitude of the normal force is basically the coefficient of the static friction. It is termed as mu s. Then the magnitude of the force of the static friction is given as mu s times n. N is the normal force, mu s is the coefficient of the static friction. Then the static friction is given by this formula. It has been determined experimentally that the mu s, the coefficient of the static friction, has these values for different surfaces. You can see the coefficient is a fractional value thing, and its value changes from very small value as 0.04 and having very large value as large as 1. So different surfaces show different static friction coefficient, and you can see here wood on wood. If there are surfaces in two objects try to move on each other, then the coefficient can vary from 0.25 to 0.5. Similarly, the coefficient of kinetic friction has been measured, and it is the coefficient which tells us how much friction will be due to the motion. The coefficient of kinetic friction is slightly less for all the cases when compared to the static friction. These values must be treated as approximate values, and they are indeed only the estimates, the experimental estimates. They have errors. The actual coefficient of the friction for any pair depends on the conditions. And the conditions can be the cleanliness of the surfaces, the temperatures, the humidity, and the pressures. So we must keep in view that these are the tentative values, and one needs to determine values for their own problem. And sometimes these estimates gives us a good approach or the good guess of the forces involved. The coefficient of friction for the kinetic friction is basically also defined with the help of the ratio of the magnitude of the force of kinetic friction to the magnitude of the normal force, and it is the coefficient of kinetic friction given by mu k. If the force is represented by Fk, then and the normal force is represented by N, then the Fk, the coefficient of the kinetic friction, is equal to mu k times n. The coefficient of the kinetic friction and the coefficient of the static friction both are dimensionless quantities, and each is the ratio of the magnitude of the two forces. Usually, for a given pair of the surfaces, we have seen that the coefficient of the static friction is always larger as compared to the coefficient of the static friction. Actual values depend upon the nature of the both surfaces and the conditions of the both surfaces in contact. So let's do the example on friction as well. This block is resting on an inclined plane. It is making an angle theta with the horizontal surface, and the angle of the inclined is raised. It is found that the slipping just begins at certain angle of the inclined plane. What will be the coefficient of the static friction between the block and the inclined plane? So we have to see this example is also telling us how to determine the coefficient of static friction experimentally. So the force acting on the block consists of this gravitational force, and then there is a normal force, and then there is a static frictional force Fs. Now, this static friction is not allowing this component of this force, the gravity force, that the block should go down. Block will keep on standing here until this force due to the gravity, the component of the force due to the gravity becomes large enough to pull it down. So force acting on the block consists of two important forces. The first is the weight of the block mg. The normal force exerted on the block by the inclined surface is n, and the force of friction exerted by the surface is Fs. So we resolve the forces into components, x and y components, and then we find out that the frictional force, which is in the positive x direction, minus mg sine theta, is the net force along x-axis. Similarly, net force along y direction is n minus mg cos theta. So we can say when there is no motion and no acceleration, ax equal to 0, ay equal to 0, just before the motion, this is the case, and we write it down and balance, then from the first equation, we find out that Fs, which is equal to mu times n, mu the coefficient of friction, static coefficient of the friction, multiplied by the normal force, then we can find out the mu s as the normal ratio of the static friction to the normal force. And substituting these values, we find that this becomes the tangent theta, tangent of the angle. And from this, we can find out the angle at if it starts moving at the 15 degrees, then the coefficient is 0.27. And so measurement of the angle of the inclination at which the slip starts occurring provides us a very simple experiment that at this angle, the break of the forces occurred. Therefore, the static coefficient was just balancing the force to the force of gravity. So we determine the coefficient of static friction through the angle of inclined plane, and this is the way to measure for any surface. Uh, as we have seen that the wood on wood, or a wood on plastic, or plastic on wood, or steel on wood, we can have any surfaces, and we can find out the experimental results. Let's do one more example, and we consider an automobile which is moving along a straight line on a horizontal road with a speed v naught. The driver applies brakes and brings the car to halt without skidding. If the coefficient of the static friction between the tires and the road is mu s equal to 0.3, what is the shortest distance in which the automobile can be stopped? So first of all, we will have the free body diagram. The car will be treated as a dot point of a mass m, and on which the normal force is the n, and the force due to the gravity is m into g, and then there is a because of the contact between the tires, there is a force of friction. Tires and the road contact makes this force of friction Fs. So let us balance. The first balance gives us that the net force along the horizontal direction is minus Fs, which is in the negative x direction, and it is equal to mass times acceleration. The normal force and the mg, normal is in positive direction and mg is in the negative direction. So n minus mg is equal to mass time ay. So from the first equation, ax is equal to f s divided by m, and the mu fs is the static friction force, and this force is equal to the mu s multiplied by the normal force. But you can see from this equation that m into a y is 0, therefore normal force is equal to mg. So I have written here mu s multiplied by mg, and then it divided by m gives us the acceleration, which is mu s times into g. So to find out the stopping time, we must use the kinematic equations. V final is equal to V initial plus A into T, and it is about the x direction motion. So all have the subscript x. Now car moves with the velocity V naught, and it ends with the velocity equal to 0. Therefore, time can be calculated from this. T is equal to minus times V naught initial velocity divided by AX. And AX we have already seen as a mu into G. Mu S is the static coefficient with a minus sign. This comes from the previous equation. You can see minus mu S into G. So coming back to this, the time has been estimated. Now we try to find the stopping distance, and we can use the kinematic equation. The final distance is equal to the initial position plus the initial velocity times t plus a into t squared divided by 2. All are along the x direction. So the displacement, we can say the final position minus the initial position is equal to this, and here the t is the main unknown quantity. We substitute v naught instead of the t, v naught divided by mu into g, and simplify this equation. If the initial velocity is 60 miles per hour or 27 meters per second, and the coefficient is 0.6, then we can determine the distance as 62 meters. And you can see that this equation do not have any value of mass m. So for any mass, for any car size, this will be the distance after which it will stop. And it depends, of course, on the static friction coefficient, which means it depends on the frictional force. So the tires and the road condition will determine how much distance it will travel before stopping. So we have several examples at the end of the chapter. So we can go through those to see how the Newton's laws are applied, and how we can find out the normal force, the tension, the frictional force and also the displacement and the velocity and the acceleration. We stop here. We will see you in the next lecture. Thank you so much.